All right, let's take a look at today's lesson. We are going to be looking at limits. We have talked about limits before, so we're going to talk some more about limits. There are really three main ways to find a limit. Today we're going to look at two of them, numerically and graphically, and then on Monday we'll look at algebraically. So there are three main ways to find limits. We'll focus on two of them today. So let's remind ourselves about the limit notation and what it means, and then we'll get into our examples. So if you recall, this is what a normal limit notation looks like, and basically it's a limit as x approaches a, whatever that value is, of f of x equals some number L. That's just the typical way that a limit is written. We've talked about one-sided limits before. The little plus right up here, it looks like an exponent. That means coming from the right-hand side. And so it's just a one-sided limit. We are not really even considering the other side. If it has a little subtraction sign up there, it's coming from the left-hand side. And so that's just a reminder of what that notation looks like. This is a pretty big deal. It's actually it's a pretty big deal in that this limit, the full limit, this is what we would call the full limit. The full limit only exists if and only if the two one-sided limits approach the same value. And that's just kind of like common sense. That makes sense that the limit is only going to exist if you're approaching the same number from the left and the right. But we really write it out in formal. We use this statement right here as one of the proofs, one type of proof of a limit not existing, as we say this: the limit from the left and the right don't equal each other. So that's going to be something that's pretty important to us. So on the next page we have some examples, and the first type is numeric. So hopefully you have your calculator with you. A numeric is basically it's using a calculator. It's using numbers. It's one of the, for us in calculus 1 and 2, it's one of the least used techniques of finding limits. We don't use numeric that often, but it is a viable technique, and we need to understand how to do it. It involves a calculator. So let's look at our first example. They're asking us to find the limit numerically. What it means to find the limit numerically is it means that we are looking for a number pattern. We're looking for the numbers to approach a particular number. So if you look at this one, this particular limit is where x is approaching 1. This table was given to us. Sometimes they give us a table, and sometimes we have to create it. So let's talk about how would we create a table. If we were asked to do a numeric limit, how would we create a table? What would we do? Well, we would focus on the x value that we're approaching, and we would want to get close to that x value on either side, on the left and on the right. If I were going to do a table, I probably would start out, just myself, I would probably start out with these three coming from the left and these three coming from the right. That's what I would probably do. And then if I can't tell the pattern well enough, I would just keep getting closer and closer until I could tell. Okay, that's what I would probably do. So they actually gave us the values to use. So let's go ahead and go to our calculator. And we've talked about this technique before, and I'll continue to talk to you about it because it's it's something you need to be comfortable with. You'll be using it in calculus, so we want to be comfortable with this technique, so we just practice it over and over again. So what we do is we're going to put that equation that we saw over there, the limit, that equation was, x minus 1 over x squared minus 1. We're going to put that in y1. So alpha y equals inner is giving me a fraction bar. And so then I'm going to put x minus 1 in the numerator. And then in the denominator, it's x squared minus 1. Okay, so once I have that in there, I'm going to use it in a blank screen. I'm going to reference it all the time, so I don't have to type it in over and over again. Now, there certainly are other ways to do this. You could use a table and such, but I just want us to be comfortable with this technique, again, because it applies to our work next year. So I would go to a blank screen and I'm going to pull down the Y1, so that's alpha trace. And see how I have all my options over here on which Y, wherever I put the equation, we put it in Y1, so I'm going to choose 1. And then that's of, and let's just, our first was 0.5. And so then we have our answer at 0.5. This is basically 0.6 repeating. So what I do is I go up and I'm going to pull down this again, and I'm just going to change the number. So pull that down and change the number to, what, 0.9. And then I get our next value, 0.52631. We typically want to go out at least 5 decimal places. On the homework, I want to say it says 5 or 6 decimal places. Just be sure you read the instructions to see what it's saying. I opened up that homework last night, so it's available. So we would just keep going like this. Okay, I'm going to kind of stop here. I think you can see the calculator input, and I'm just going to go to the table. I'm going to write down the values for you because I've already done that. So I'm just going to, let's go fill these values in, and let's see if we can determine a pattern. So 0.5, 0, I'm going to go out 6 decimal places. You can round or truncate out that far. It's really up to you. Either is acceptable. Let's see, 526316. That's a 5. Sorry about that. 0.99 is 0.502513. 0.999 is 0.500250. And then 0.9999 is 0.500025. I think we can tell this number pattern right here coming from the left. It definitely looks like it's approaching a half, doesn't it? I mean, that's a pretty clear numeric pattern. And that's why what we do with numeric limits, doing them numerically, is we're looking for a numeric pattern. That's our goal. Now, so let's complete the chart from the right, starting at 1.5. That's at 0.4. Then at 1.1 is 0.476190. Then 1.01 is 0.497. 512. Then at 1.001 is 0.499750. And lastly, at 1.0001 is 0.4, and then there's 3975. So I think numerically this is very clear. This is a clear pattern. And some students struggle with, well, what do I write? You know, do I write 0.5000? Do I write 0.4999? No, you want to write what you believe that it's approaching. And if you're not sure, you just need to keep getting closer and closer until you're sure. I'm pretty sure this is approaching a half. That's what it looks like to me. And so that's what I'm going to write. I'm going to actually write a half. I'm not going to put those weird decimal, approximations. I'm saying that this is approaching a half. And in your homework, most of these have fraction answers, like 1/2 is how you would enter it. Okay. So now number 2, are we okay with that, with the numeric pattern? So this is a normal numeric limit. This is normal. Now I'm going to show you not normal. Okay? Of course, you're going to have to see something not normal, right? Number 2 is not normal. So let's look at number 2. I'm going to go and input this. We're just going to do a little bit more calculator work. I think you're pretty comfortable, but I just want to do just a little bit more. So let's go to our calculator and let's input that equation, which was, and be sure you're in radian mode. I think I've already checked, but be sure you're in radian mode. This was sine of, and then there's a fraction, alpha y equal enter, sine of pi over x. So pi over x. Okay, so let's go to our blank screen and let's, you know, I changed what was in Y1, but I can still use that notation. It's gonna pull what now is currently in Y1. And so they want us to do Y1 of 1. And that is 0. Okay. Alright, let's go up and pull this down again. Let's keep, so now Y1 of 1/2. So 0.5. That should be alarming to us, right? Is this a straight line at 0? This is not a straight line. Okay, that's weird. Well, let's just do one more. So we already noticed there's something strange, right? We already noticed there's something strange before we're even much into it. 1/3. So alpha y equal, so 1/3. Okay, so for those of us that get confused by calculator syntax, I understand why we might be confused. This is 0. Okay, a 0, right? If you think about it, if you have a -1 times 10 to the -13th, isn't that like 13 zeros and then a 1, right? That's just 0. So the E thing, I don't know. We don't do any calculator syntax answers in math. I know they do in some of the science classes, but we don't do that in math because it's not mathematically correct. So we don't. You can write scientific notation if you want to, but really that's just 0. Okay, so we're getting a bunch of zeros. That's really concerning. So let's look at the graph. So I'm going to, we only care about 0, so I'm going to change my window. I want to look at like between -1 and 1. I'm not really interested in looking at the whole entire graph because I really only care about what's happening at 0. And then let's graph that. Oh, okay. That's a little weird. It seems to behave like a sine or like a trig graph until it gets towards 0. Then it looks kind of weird. So, well, let's just zoom in closer, see if we can find out what's going on. So we're going to zoom in, and I'm going to zoom in at 0, 0. So let's do that. Okay, that's not any better. It's still looking kind of bizarre. Let's just zoom in one more time. Maybe we can get a better look at what's going on. So we're going to zoom in, one more time to 0, 0. Oh no, we're not making any progress. Right, it's getting worse and worse. So this is an unusual one. This doesn't happen very often, but we need to know what that means. What that means is that the limit doesn't exist. This is one where the limit is not going to exist due to oscillating behavior. And we just don't have many crazy things like this, right? I mean, we don't normally see this. And if you get in closer and closer, it's not going to get any better. It's just going to get more and more wild. All right, so this is an unusual one. I want you to see a normal numeric limit and then a really weird one so that you could be on alert. So what we would say is, you know, basically this whole chart, if you go in and fill out this whole chart, they're all zeros, which should make you think, there's something wrong there, right? That's not a straight line. This is not a straight line at 0. I mean, that's not what that function is. So we would say that this is D and E, and every time you tell me D and E, you have to give me a reason. We're just not going to write D and E everywhere and be done with it. Like, oh, it doesn't exist, I'm moving on. No. Why? Why doesn't it exist? You need to tell me why. And so in this particular case, the reason it doesn't exist is due to oscillating behavior. That is a thing. All right, so it's D and E due to oscillating behavior. And there's our second numeric limit. Okay, how are we with that? Everybody okay? Okay, now let's move to the other technique that we're going to be looking at today, which is solving it with a graph, graphically. Okay, so once we get this, I think the biggest hurdle for solving it graphically in times past and experience, I will tell you the biggest hurdle is these points right here. These points just kind of freak students out. They don't know what to do with the points. They don't know how, does it have anything to do with the limit? What is it? And I will tell you, these points right here, okay, just very clearly, never, ever, ever have anything to do with the limit. Ever. Okay. They are never the answer to a limit. Because they're just these things off in the wilderness, right? Limits are part of a curve, right? The answer to a limit is a part of a curve. It's not some dot out in the wilderness. Okay, there's no four-wheeling in limits. Okay, we do not get off the path on a limit. So what these are function values. That's their purpose, their function value. If I asked you, and this doesn't ask you, but we're just going to add one. If I wanted to know what f of 2 was, you would go to an x value of 2 and you would find the function value there, which would be that point. It's 2. Does that have anything to do with the limit at 2? No, absolutely not. Nothing to do with the limit. That is probably the biggest confusion students have on limits graphically, are those little random points. Okay, so if you just kind of get through, they are never ever the answer to a limit. They're just function values. Then I think this will be easy. So let's just kind of work through it. We're going to look at an x value of 4. So here's 1, 2, 3, here's 4. And what I'm going to do is I'm going to do this formally. I'm going to approach 4 from the left and the right. Okay, so you can see what's going on. Let's come from the right. What I do is I attach myself to the curve and I'm headed towards an x value of 4 from the right. What y value am I approaching as I'm headed towards that x value from the right? 3. Okay, we okay with that? Now I'm going to attach myself to the curve and I'm going to head towards that x value of 4 from the left. As I'm headed there from the left, what y value am I approaching? 3. Okay, I'm approaching a 3. That means the limit is 3. Now, do we ever get to be a 3? No. And they're probably very sad about it, actually. The limit's probably like, oh, I'm so close. I'm so close. I get to be 3.1, 3.111, 3.11111, you know. I get to be 2.9, 2.999, but I can't really get to 3. That's okay. And for a limit, you don't have to actually attain the value. You just have to approach the value. That's the kind of a little strange thing about a limit. You just have to approach the value. You do not have to attain it. So it's 3. Okay, we approach from the left and the right. It's 3. It's not this. What is this? What does this point represent? The function value, right? This is the function value right here at 1, 2, 3, 4. If I asked you what f of 4 was, you would not tell me 3. F of 4 is not 3. The limit is 3, but f of 4 is actually 6. Okay, so hopefully we have that really separate, distinguish in our brains, right? We know those two differences. All right, so let's kind of move on. So now let's look at the limit as x approaches 0. So here, x is 0, basically coming from the left and the right, we're approaching a 2. Everybody okay with that? There's nothing weird there. Now let's look at 2. Okay, that's definitely weird. The limit doesn't exist there. And when the limit doesn't exist, you always have to tell me why. Always. So the y actually is here in E and F. So let's do those. Now this right here is the y. We're going to look at what's happening coming from the left and the right for 2. So let's focus on this one. Let's look at 2. So we attach ourselves to the curve to the left of 2. and we follow the curve. Where's the curve leading us? Where the curve is taking us? Taking us down to negative infinity, right? So as we approach 2 from the left, we are going to negative infinity. So now let's go from the right. Let's attach ourselves to the curve on the right. Okay, we do have to skip a pothole, but that's okay. We skipped it. We just went on. So what y value am I approaching coming from the right, headed to an x value of 2? 5. Okay, are those values the same? No. That's why the limit doesn't exist, is because the two values coming from either side are not the same. So we say the limit as x approaches 2 from the left of f of x does not equal the limit as x approaches 2 from the right of f of x. Now, if you don't want to write it out in, this kind of notation, you can say it in words. You can write me a sentence. The two, each side doesn't, whatever, from the left and the right don't equal each other. The limit from the left and the right don't equal each other. You can say it in words too. But that's the reason why. Okay? That's our why. So let's go back. We kind of skipped over poor little d. So we're going to 1 from the left. 1 from the left. That's just a 0. We're comfortable with that? And that there's nothing weird going on there. 1 from the right is 0. Okay. And now negative 1. Ooh, look what's happening at negative 1. So from the right, I'm headed to infinity. From the left, I'm headed to infinity. So this is infinity. Okay, how's that? We okay? Okay.